SwayamPrabha. Digital India. Educated India.
Been discussing about the different types of growth modes during solid to liquid transformations. Just a recap of the discussion which you had in the last class. You know, solid liquid interface can be of two different types. The one which can be atomically smooth, the other one is which can be atomically rough. Okay. So depending on the type of interface, the growth modes will be changing. Right. So in case of rough interface where the interface is jagged, what you need is basically a step or a ledge or a kink even on the ledge for the growth to proceed, and this is very routinely happen in case of various metalloids like silicon, germanium. So this kind of growth is basically known as stepwise growth. And as you see here, there is a ledge on the surface. This ledge basically forms because of the surface nucleation, and which I have discussed in the last class. And then this ledge can also bend and form and kink, and because of these kinks, then atoms from the liquid can arrive nicely and sit on these positions known as J, marked as J here, and then make the further progress of this step in this direction. Slowly steps will move like this, and so the one layer of this solid will be liquid will be converted into one layer of solid, and then further goes, so things happens. And surface nucleation is the main mechanism for the ledge creation. Ledges are created because of the surface nucleation. Surfaces which are basically kind of a very rough in this way, so there can actually have such a nucleation happening, and that this can lead to formation of this step. Well, the step on the surface can also be created by screw dislocations. A screw dislocations is shown on the surface, and as you clearly see, there is a step here which is bent. So because the atoms can go and sit there, the screw dislocation will start rotating itself to keep these positions intact. And this is normally happens in screw dislocations. Suppose you have edge dislocation, then edge dislocation will be slowly converted into a dislocation free structure, but for a screw it is not possible because of its nature of bends, and this can lead to the further growth of the phases, further growth of the systems in the positive directions. You can also have a new mechanism, or it is already there, in what is known as twin plane reentrant edge, or TPRE. This was proposed by Professor Wagner long back, and later on substantiated by D.R. Hamilton and R.G. Sneden-Sticker in 1960s actually. What you can have is basically you can have a twin formation on the surface, and when these two twin planes meet, they create a reentrant edge. And this reentrant is shown here. This is the reentrant edge. You can see here. It's basically there are two ridges here which are actually 218.9 degrees, and these two ridges, when they meet together, they form a reentrant angle, and this reentrant angle is at an angle of 141.1 degrees. So enhanced liquefaction on this edge, on this groove actually, not edge, groove is easily possible when the liquid atoms comes and sit there and join the solid. These are the actual pictures which can happen in case of silicon. Silicon crystals are basically like that, and therefore there are varieties of ways such a kind of growth mechanism is possible, like dislocation mediated or twin mediated, or even by the surface nucleation. But on the other hand, for the atomically smooth surfaces where there is a diffuse interface, that means there is a huge layer between the solid and liquid, atoms actually can easily sit on the surface and grow, and that kind of growth is known as a continuous growth. And this growth, which is basically by twin or the dislocations or by surface nucleation, is basically known as stepwise growth. So now we can actually calculate, it is possible to calculate the growth rate, and all this growth rate will be function of undercooling. So, I am not doing the whole mathematics here, it is there in the book, or you can actually consider each of these cases. I have done for the continuous growth, I have shown you this is directly proportional to delta t. So, therefore, the growth rate V is basically a straight line for the continuous growth, and for the spiral and the surface nucleation dominated growth, they are actually not directly proportional to delta t, but they are proportional to some functions of delta t, and they are basically exponential function of delta t as you have seen from the nature. So, basically the growth rate by surface nucleation is very slow at initially, it requires a larger undercooling. That is because you need surface nucleation, and nucleation requires to create a new surface to be generated, and that is why you need more diving force, and the more diving force means more amount of undercooling. On the other hand, spiral growth, which is basically because of the screw dislocations, does not require much undercooling. You can see this undercooling curve is pretty low. So, and then starts off and it goes, and then finally it's at a higher undercooling, this growth can be, all the actually growth rates will be same as like a continuous growth. That is what you see here and there. This is a basically very important plot in the sense that at low undercooling, continuous growth rate will be the maximum, but high undercooling, all the growth rates will be similar, okay, same. In the intermediate undercoolings, normally the spiral growth rate will be higher than the surface nucleation growth rate. So, depending on the amount of undercooling available in the systems, the growth rate for these systems can vary. System can choose depending on undercooling which growth mode to be adopted. Okay, so that is fine, that is about the different growths, but what is the growth morphology? You know, solidification means what? As the liquid solidifies to a solid or forms a solid, there is a latent heat evolution at the interface. Now, because of this latent heat evolution, because latent heat is getting released, that heat must be conducted away or it may be convected away by the liquid or the solid to the liquid. Depending on how the heat transfer happens, the interface morphology can change. And we are going to discuss for the case of a pure metal, okay, what happens to pure metal when these kind of situation arises. Again, we are going to discuss two cases. First case is basically for a solid liquid transformation in which the temperature gradient is the positive in the liquid and the solid, but there is interface between the solid and liquid. Remember, heat transported depends on the temperature gradient developed in the system. So, because of the difference of temperatures from one place to other, the temperature gradients do develop in the system. So, let us suppose you have a solid liquid, you can see this is solid, this is liquid, and as the liquid solidifies and forms a solid, latent heat is released at the interface. So, therefore, if the situation is such that the liquid has been poured into a mold and the mold was at room temperature and liquid was at very high temperature, because of this solid forming at the mold wall, the heat will be transported to the mold wall. In such a case, liquid will be always at a high temperature than the solid, and as the heat is getting transported through the mold wall, so therefore the temperature gradient develop from the liquid to interface to the solid. And this interface is shown as a line here, you can see here, or you can see here, or you can see here, this is a line. Now, as you see here, because temperature gradient is high, the temperature gradient is positive rather in the liquid. So, what will happen? Because of that, the heat will transport from the liquid to the interface and to the interface to the solid and to the solid to the mold wall. This is the mold wall, suppose. That is how the heat transport will happen because of the nature of the temperature gradients created. Now, under such a situation, if I have a small protrusion created on the surface, okay, what will happen then? Well, as you can see, suppose if I draw this picture here, and this is my interface, okay, this is solid, this is liquid, temperature gradient is varying like this, okay, that is the temperature gradient between the liquid and the solid, and let us suppose this point is marked as a B, and suppose I mark this point as A, and this is my interface, correct. Now, I can clearly see that B will be at a higher temperature, okay, this is point B if I mark it here. So, B temperature is TB, okay, I marked it here TB, and A, which is on the interface itself, its temperature is TA, I have marked there, okay, and the melting temperature is given somewhere there, okay, this is Tm. Now, this is the temperature profile because there is a protrusion created on the surface. If this is what the temperature profile, now what will happen? We can clearly see the temperature of B is higher than temperature of point A. That means the total undercooling is nothing but delta T is nothing but Tm minus the temperature T, and for the B is basically Tm minus Tb, for A it is Tm minus Ta, and A is lower than Tb, so therefore undercooling at A is higher than undercooling as B. And because the temperature of B is higher, because Tb is higher than Ta and undercooling is low, so therefore even if this protrusion is forming there, it will go away. Why? Because it will not feel undercooled more than this flat interface. So because it is not feeling undercooled more than this flat interface, it will not able to grow, because growth is dependent on the amount of undercooling available. If the undercooling available to the point B is lower than undercooling available to point A, so therefore A will go faster, and that is why this interface will become remain as a flat even it grows from position A1 to position 2. And in this process any protrusion which is forming on the surface will be melted away. So this one will vanish, this thing will vanish as the system moves from one position to position 2. And this is exactly what happens when you have a positive temperature gradient in the liquid. This situation is very common in welding. Suppose you are using a heat source to make the weld pull. It may be laser or it may be anything else, electron beam or a gas or a arc. So because we are using a heat source on the top on the joining positions, so therefore the temperature gradient in the liquid will be higher. It is very simple, because you have a heat source placed on the weld joint pool, so therefore the temperature the heat is provided on the surface, and because of the temperature from the bottom of the pool to the top of the pool will be positive, temperature gradient will be positive, and the same situation will arise. And because of this, in all these welding or situations, temperature gradient is positive in the liquid and interface do move like a flat one, or continuous growth happens. Okay, interface will not be forming such a kind of protrusion on the surface. That is very clearly observed even in experimental conditions, and this is why positive temperature gradient will induce continuous growth, or the growth of the flat interface across solid liquid interface region will be happening like a continuous manner, and this will never be we will never be able to form any protrusion on the surface. On the other hand, the situation will be completely different if I have negative temperature gradient in the liquid. This situation is more prevalent in industrial conditions. Suppose I have a mold, okay, which is a little bit heated up. It may not be at room temperature, it is slightly higher heated up, and we pour a liquid hot metal actually into this mold, and because the temperature in the liquid in the mold wall is little higher, so because of that any solid forming on the mold wall will be at a temperature higher than the liquid temperature. Obviously when the solid forms in the mold wall, the latent heat will be released, and the latent heat is transported to the liquid. Because of these negative temperature gradient, the solid will grow much faster in the liquid as compared to the one which you have seen in the last case. So nonetheless, even if such a situation arises in the liquid, when the temperature gradient in the liquid, you can see this is the distance x, that is what is shown here, there is a temperature T. So therefore you can see the slope of this curve is negative. As the slope of the curve is negative, what will happen to the same situation which I have drawn there? Let us draw it here. Let us suppose I have a flat interface and there is a protrusion created there, okay, and I am drawing the interface here, okay, and the temperature gradient in the solid is positive, but temperature gradient in the liquid is negative, okay, and this is temperature, this is distance x, okay, and let us suppose that this is point B and this is point A, okay, the point B is on the protrusion, point A is on the interface. So, point B and point A, point B temperature is where? Then point B is here, the point B temperature is the point A is temperature is this one TA, and point B temperature will be somewhere there. Okay, this is point B. You can draw the point B there this way. Fine. So, what you see here very clearly, because of negative temperature get in the liquid, the point B temperature TB is less than TA, and therefore the point B is undercooled more than the point A, because undercooling is again defined as a Tm minus T. Now, as TB is lower than TA, total undercooling delta T is higher on point B than A. As B is getting undercooled more than A, so B will have more diving pores to grow. So, therefore, the protrusion which is formed on the interface as shown here will grow, and this protrusion will lead to the breakup of the interface which was flat in the earlier case when the temperature getting the liquid was positive, will now break up and form this kind of large protrusions on the surface. Remember, these protrusions can easily form like this. Suppose if I draw a simple picture, I have suppose two protrusions created, okay, and this is point B, this is also point B. Let us suppose this is a point B prime, okay, and this is point A, okay, and if I draw a vertical line, and this is suppose point C, okay. Now what will happen? You clearly see that at point C the liquid is more undercooled than point B, okay. That is obvious, because the point B is basically sitting on a solid surface, okay, because this is already a solid, and because it is already solid, any further growth of the solid will lead to revolution of the latent heat, and this latent heat whatever getting evolved here because of its solidification happening further will heat up the liquid nearby point B. So, therefore, C which is far away from point B prime here you can see here these two are the point B prime, which are far away from these two positions will be more undercooled, and because it is more undercooled, so what will happen? It is very easy to form another let me draw it firstly. So, what I have done is like this, I have drawn two protrusions and I have drawn 2 points B prime and B prime here, and then I have drawn a C point C, this is point A. So, as point C is basically getting undercooled more than the point B prime, 2 B primes here, obviously A is at a high temperature. So, the question of A does not arise. Just to show I have drawn A. So, because of this high undercooling and point C sorry compared to point B prime, the protrusion will be forming like this and growing, okay. It can go like that. So, finally what happens? So, finally if I actually have to draw the whole picture, so it will be like a tree like structure will form, and this tree like structure which forms on the interface are known as dendrites. Dendrite is basically a word originated from a Greek word known as dendron, and dendron means tree. So, finally we can actually create a very large tree like structure like this. This is a tree, right? It looks like a tree. You can actually create sub branches of the tree, or even furthermore sub branches like this in the same way what I discussed just now. And this is what is known as a typical dendrite in a solid when the liquid transforms to a solid. So, obviously we are discussing a pure metal. So, the only thing which is important here is the transport of heat, because there is no alloy, there is no solute. So, therefore, thus is very clear that the which will be forming because of the solidification of pure metal will be basically the growth of that will be dictated by the type of temperature gradient which develops in the liquid. If the temperature gradient is positive in the liquid, no dendrite or tree like structure will form. Even if they form, they will melt back or they will be vanishing from the system. But only when the temperature in the liquid is negative, please remember this word, temperature in the liquid is negative, that means the sign of the term del T by del X that is what is your temperature gradient, right, del T by del X or dt by dx in a one dimensional case. When this is negative in the liquid, this is liquid, then only the dendrites can form, and dendrites will form because of the mechanism which I told you just now. So, such dendrites actually known as a thermal dendrites, okay, because they are forming because of the heat transport. They are known as a thermal dendrite. So, their growth basically depends on how fast we can transport the heat. Okay, that is the basically the important aspect. Now, this fast or slow transport of the heat will depend upon what is the temperature value of the temperature gradient. The temperature gradient is very high, then heat transport will be faster, as you know, because this is basically given by the Fourier's law. The heat transport or the flux depends on the temperature gradient, just like a diffusion equation. So, therefore, the higher the slope of this curve on the liquid, the faster is the heat transport. Remember, from the liquid to the interface to the solid. So, again if I want more heat transport from the solid to the mold wall, I need a very high temperature gradient. So, therefore, if I draw such a kind of a curve like this is where the temperature gradient are much higher in the both in the liquid and solid. So, therefore, because of that the heat transport will be very fast both in the liquid and solid, and this will lead to faster growth of dendrites, and that is what is done in the rapid solidification. In rapid solidification systems like melt spinning or even atomization or thermal spray, this exactly what happens. The temperature gradients are negative in the liquid and temperature gradient values, because absolute values are very high, and because of that heat transport is also very high. Remember, these dendrites do grow along certain crystallographic directions, they do not grow any odd directions. Normally for the cubic crystal these crystallographic directions are 1 0 0, okay. So, and there is many reasons for that. So, we will not discuss in details about why they grow along 1 0 0 directions, but the crystallographically low index directions is what has been found, which along which the dendrites grow. For the cubic, for hexagonal this is for the cubic, for hexagonal is basically 1 0 1 bar 0 or 0 0 0 1. These are the two directions which has been found for a ACP crystal. On the other hand, 1 1 0 is found in tetragonal crystal. So, for every crystal structure there is a well defined growth directions normally observed when the dendrites grow. So, therefore, if this is 1 1 0 direction, so this will be perpendicular to that, okay, this one, this will be 0 1 0, okay. So, in a 3D, that is what we see in a 3D structure, there will be 6 arms of the dendrites, and because in a cubic crystal there is 6 1 0 0 directions, that is very clear. If you draw a simple cubic unit cell, there are 6 1 0 0 directions. This is 0 0 1, this is basically 1 0 0, and this is 0 1 0. So, I can always have 6 directions like these, okay. You can clearly see the 6 directions 1 2 3 4 5 6. That is why you always see the 6 arms of the dendrites in the real 3-dimensional pictures. Okay, before going into that, let me first show how things happens. This is taken from Riddle, Physical Metallurgy Principles. It's a very interesting book. You can see here this is a typical tree-like dendritic structure in a solid, and these worms, these are known as a primary, because this is what that's what again I draw. This is known as a primary. This is known as secondary. I am drawing only one part, okay, and you can also have a tertiary, primary, secondary, tertiary. You can see here it's shown there. So, they are all at a 90-degree angle each other in a cubic crystal, because 1 0 0 directions are at 90 degrees with each other, that is why, and this is observed in the real situations. Well, the reason behind this is surface energy between solid and liquid, which is the most important aspect which play a role. In the solid crystals, actually surface energies are anisotropic. The interfacial energy between solid and liquid is basically anisotropic, and because of that they preferentially grow along 1 0 0 directions. This is very important, that most of the crystals or the dendrites they grow is basically 1 0 directions. Okay, now I will show you some pictures before I go into the next class, just to show you some dendritic growth, dendrites, where next class will be based on things, real pictures actually. These are microstructures. This is basically taken from a cast aluminum copper alloy. You can clearly see the different dendrites here, one here, sorry, one there, okay, it's very clear and can be seen. This is one, this is another one, this is another one, okay, many sets are there actually. So cast structure will consist of lot of these dendrites. This is alloy although, because in pure metal showing a dendrite is very difficult. Basically the way we show the microstructure is by using etchant, or by basically using some etching process. Etching process means we use basically a chemical either acid or a base or something to react on the surface of these alloys or metals. You know, in pure metals normally reaction will be uniform, but in alloys reaction will be preferential. Some elements will react strongly than other, and because of that it will leave the structure nicely revealed under optical or SEM microstructures. So in a pure metal also dendrites are seen, but they are actually known as thermal dendrites, as I told you. Like this one is basically copper tin, which is a bronze, and as you see here these are the dendritic structures which are revealed. Okay, there is some other phase beta which is present as the yellowish color phase is basically the dendritic phase, and you can look at some of these places and see the dendritic structure develop. You can see here this is what the dendrites, okay, so everywhere, and in between the two dendritic arms something else has formed. That is why it is little bit cumbersome to observe, but you can make it out by this way. Okay, that is what is dendrite is. So many things are there. Now we will go back dendritic structure later, but to show you how evolution happens actually in dendrites, initially the flat interface will be broken. You can see here this is the flat interface, some kind of protrusion have formed, and these protrusions have grown up, and they have grown up bigger, they are bigger, and finally they form a structure, and this is basically known as a cell, because cell is nothing but a dendrite without any side arms. The moment you develop a side arm it is called a dendrite, but the moment you do not develop a side arm it is called a cell. Basically they looks like, this is dendrite, this looks like a basically the honeycomb structure. That is what is shown here, okay, hexagonal cells in a lead tin alloy. You can see each of these is a hexagonal network out of the solid wood interface. Lead tin is a low melting point solder or material basically, so you can actually do that very easily. So the cells can be like one I drawn, this one, or it can be like hexagonal units, okay. It is possible to have that, but origin of the cell is basically because of these formation of these kind of small perturbations which are basically there, or basically on the surface you form a kind of such a kind of things, and these things then grow because of the driving force, high driving force available to them. I just discussed just now. So in the next lecture we are going to discuss what will happen with to the heat transport, and how whether you can put it in mathematical form, and also when you have an alloy, because in case of alloys you have a solute which will also be rejected in the liquid, and because of the rejection of solute you have a heat transport and a solute transport, both are present, and this is going to be changing the whole situation differently than what you have seen just now.